So we were discussing the Cartan killing form and this was finally the theorem 12.5. It is mentioned here 12.5. This is the number 1. Which the number 1, which basically says that 2b h alpha h beta divided by b h alpha is equal to p minus q, where p and q are, so one is considering alpha string through beta. So that means the string starts from beta minus p alpha and so on, and goes on to beta plus q. So there is a beta, and then in units of 1, beta plus alpha all the way to beta plus q alpha, and beta minus alpha all the way to beta minus q alpha. So this is the string, okay? Which means that these are the only roots which exist. The next one doesn't exist. Beta plus q plus 1 alpha does not exist. And similarly, the one before that does not exist. So this is the bound. And then we found that once you have this p and q, this quantity, 2bh alpha h beta divided by bh alpha h alpha is equal to p minus q. This is very important. It's a very important statement. Okay. So this was, I remember from the way we defined, this was nothing else but 2 alpha beta divided by alpha, right? Remember, those are the roots. So we defined the inner product between the roots by going to the co-roots and defining these are the co-roots, right? H alpha was the co-root corresponding to alpha, and H beta was a co-root of beta. And this was a definition. This product, inner product, was just that, B of H alpha H beta. So that's a very important statement. And then using this, we showed that the B Cartan killing form restricted to the Cartan subalgebra, a real Cartan subalgebra, By real, what do I mean? You just take these elements are, I don't know, let's call it H real. That's a real Cartan subalgebra. HR, which was basically elements of the type of the form R meaning a real number, H alpha, summed over alpha. So this real Cartan subalgebra, this was positive definite. So when B is restricted to that, it is positive definite. Okay. Which means that actually now you can really think in terms of geometrically you can think about it, right? Because it's a Euclidean geometry. It's a positive definite metric. Not a Lorentzian, the Euclidean metric. So that was a very important statement. Was there any question on this? Because I think towards the end I was rather quick because there was not much time. So maybe you. Okay, maybe I can just continue, assuming that this is clear. You know, what I was thinking of was that maybe we should meet again once, okay, after your RQM exam. No, RQM exam is on Monday, right? I mean, not this coming Monday, the Monday after, no? And then this exam is on Friday. So maybe one day we can meet in between, you know, maybe let's say Wednesday, for example. No? So that when you go through it and you may have questions, then we can discuss again. Huh? Okay. So this was fine. Now, okay, the next chapter, I skipped the uniqueness of Cartan killing form. Okay. I mean, those of you who are interested, you should go through it. But it's just when I say I skip it, not because of lack of time. You know, and if you have any, when you go through it, I mean, if you are interested, go through it. And if you have any questions, you can always come to my office and, you know, we can discuss that. But this will not be part of the exam. I mean, the things I'm not covering will not be part of the exam. But I encourage you to go through it because it's really very beautiful. The structure is very beautiful. Okay, the chapter 13. I don't have time. I mean, I can only do either chapter 13 or 14. So I would prefer to go to 14. Okay, chapter 13 is just straightforward. I mean, if you sit down and go through it, it's completely straightforward. There is nothing. You just need to do some little algebra. I mean, linear algebra, matrix, commutation relations. You know, and you should be able to prove every single statement there. I mean, to understand every single statement. So I will go through 14, and even that, not all of it. Just try to give you some flavor of the of the powerful structure we have already obtained, and then to use this powerful structure to, for example, I would try to classify all rank 2 semi-simple algebras. You know, whether or not they are coming from some classical algebras, meaning what we know of SUN, SONs, or SPN. No? In fact, we'll find that there is one example you can construct using this general formalism, which was not in the classical algebras. It was something new, you know, which is called G2. So I will try to do that. And because tomorrow I want to go through I mean, I could have done both these chapters, today one, tomorrow another. But tomorrow I want to spend some time on the spinor representations of SON. Because that could be quite useful. You have already seen the spinor representations in 4 dimension, right? But now what I will do is for arbitrary SON, you know, how you construct the spinor representation. So that's why I think I'll skip the 13 now and move to 14. Okay, so let us just call this number. This is some number, some integer. So let's call this integer. This is an integer, of course, right? This integer depends on alpha and beta, right? So I'll just use the same convention, which is here, n alpha beta. Yeah, it's we call it n alpha beta. Notice that this is not symmetric in alpha and beta. Okay, because while numerator is symmetric, the denominator is not, right? So this the first index means it is the guy alpha in the denominator. So if I take the other one, if I exchange alpha and beta, so you'll have 2. The numerator is the same because, you know, this b of h alpha, this is symmetric in these two, right? Because b is defined as a trace of the 2 adjoint matrices, right? But trace is cyclic. No? So whether you put h alpha first or h beta first, it doesn't matter. So that the numerator is the same, but the denominator now is beta. If I exchange alpha and beta there, and this will be called n beta alpha. So this is just one has to keep the position straight, otherwise, because it's not symmetric. Okay. Now some things you can immediately say. So for example, if I consider this thing here, and let's suppose I consider again this alpha string through beta, and let's suppose n alpha beta. Suppose n alpha beta is greater than 0. I mean, there are several possibilities. It can be greater than 0, less than 0, or equal to 0, right? Integers, so various possibilities. If n alpha beta is greater than 0, that means for sure, this implies that n alpha beta is greater than or equal to 1, right? Because it's strictly greater than 0, and this is an integer, so it has to be at least 1, right? 1 or maybe more, but at least it should be 1. But that means, that means P minus Q is at least 1, right? Now, how can it be? That means P must be certainly at least 1, right? Because both of these are non-negative integers, right? Because this is the way I'm labeling these guys. Huh? So both P and Q are greater than or equal to 0, right? So if this is 1, let's say this is at least 1, we are saying, then the only way it can happen is that at least P is 1. I mean, P is 1, Q equal to 0, or P equal to 2, Q equal to 1. But whatever it is, P has to be at least 1, right? So this implies that P is at least 1, is at least 1, or maybe greater than or equal. P is greater than or equal to 1. But if P is greater than or equal to 1, then in this chain, for sure, beta minus alpha exists, right? Because you start from beta, beta minus alpha, beta minus 2 alpha, all the way to beta minus p alpha. So at least beta minus alpha for sure exists. You can of course do the other way. Suppose n alpha beta is less than 0. This implies that n alpha beta is less than or equal to less than or equal to minus 1. And again, the argument, this implies that P should be, Q should be greater than or equal to 1, right? And this tells me that for sure beta plus alpha belongs to delta. Right? So just from the sign, you immediately know that if the sign is positive, sure this exists. And if it is negative, surely that exists. If it is 0, you can't say anything. I mean, both P and Q could be 0, or both of them could be equal, no? Not 0 but equal, but we cannot make any definitive statement. That one has to see case by case. Okay. In particular, you can see also from here, you can see that if, you have this object here, then you see if beta minus 2 alpha beta divided by alpha alpha, so in other words n alpha beta times this is a number times alpha also belongs to delta. I mean, here I just use this thing here. I mean, if n alpha beta was, let's say 2, for example, let's say 2. I mean, this guy was supposed 2. Then we can even say more strong than that. We can say that P is greater than or equal to 2, right? Then we'll have beta minus 2 alpha would also exist. So this is how you prove this. So, but this is almost like, you see, this is the kind of thing that we were talking about, this while reflection. While reflection is that. You remember that all these SU3 pictures, we had these nice pictures of SU3, where if you take any of these non-zero roots and draw a perpendicular here, then there was a reflection symmetry. That's exactly the reflection symmetry. Because, I mean, this object, which is 2 alpha beta divided by alpha alpha, is exactly the reflection of beta. Suppose this is alpha and that is beta, then this is exactly the reflection of that. Beta minus, you're basically looking at the projection, alpha dot beta, the alpha dot beta, which is this length. I mean, alpha dot beta will be this part here. You're subtracting 2 times that, okay? Which is exactly the reflection. So this is the reflection symmetry, actually. So if beta exists, if beta belongs to delta, then this also belongs to delta. Yeah.
But we have also seen that in lower dimensional representation, the other root is not existing.
So can you repeat again?
In 3-dimensional representation, the other roots didn't exist, and we constructed the conjugate representation.
Weights, that's our weights, yeah. Yeah, but this I'm talking about just the roots. I mean, so...
Are you talking about still in the fundamental representation?
Yeah, but no, I'm talking about adjoint representation. This is all adjoint representation. Mm-hmm. This discussion is completely adjoint. When you talk about roots, there's always adjoint representation.
This is implied when I talk about roots.
Yeah, because we have always been working with the commutator. Commutators are always adjoint.
The whole construction up to this point, it started from semi-simple algebra and was built on adjoint representation.
Exactly. Because this whole structure we're discussing is a commutative, but commutative is the same as adjoint, no? Adjoint of X alpha.
Now, by this, we can say that always in adjoint representation, the one symmetry is
That
existent.
No, I mean, actually, even there, I mean, sorry, you know, even in the roots, even in the weights, it was still true. That was, the weights also it was true. What was failing there was that for every non-zero weight, the negative of that non-zero weight was not in the same representation. But the reflection symmetry was also there. You see, I mean, if you look at the SU3, the fundamental representation was like here, the weights in this diagram are like that, right? Let's say this was the fundamental 3 representation. This also is symmetric. You see, this guy goes there under the reflection. If you look at this plane, I mean this line, then the perpendicular line plane would be this here, and again this reflection symmetry. The reflection symmetry is always there. What was failing there was not the reflection symmetry. It was just that for every root, the negative was not existing. In the adjoint, we will see, I mean, it will turn out to always be the case. If alpha is a root, I mean, we already know, if alpha is a root, minus alpha is also a root. No? So that's, okay. So this is, now, let's see. Again, I want to emphasize that the fact that we showed that the B restricted to real Cartan subalgebra HR is positive definite, right? And since this dual inner products is defined in terms of the inner products of the Cartan, right? So this also is positive definite. Okay, alpha beta is positive definite. So therefore, really, you can use all the geometric concepts that you have dealing with the Euclidean geometry. You know, so your dot product of 2 vectors is the length of this vector times the length of that vector times cosine of the angle in between. And that's the sort of consequence of Euclidean geometry. So we can apply all that. This you couldn't apply for the Lorentzian metric, you see. But Euclidean metric, you can apply that. So that becomes very powerful now. Okay. So now let's take the product. Let's take the product n alpha beta times n beta alpha. Okay. So that is 4, and just take the product of these two, 4 alpha beta square divided by alpha alpha beta beta. So this is certainly greater than or equal to 0, right? Because these are positive definite, and this is square. I mean, this could be negative. This is dot product can be negative, right? Between 2 different vectors. It depends on the angle, no? But the square will be always non-negative, right? So this is non-negative, so this is greater than or equal to 0. Furthermore, if you think of this n alpha beta as the dot product, what is that? I mean, I can, you see, what is this object? It is 2, the length of alpha, I will write it like this, length of alpha, because I now think in terms of purely Euclidean geometry. The length of alpha, length of beta, times cosine of theta alpha beta. This means alpha beta, this just means the angle between the two, alpha and beta root. That's that, divided by alpha square, right? That is n alpha beta. And here it is 2 alpha beta, same angle, cosine theta alpha beta, divided by beta square. Now take the product of these two, what do you get? This is the same as 4 cos square theta alpha beta. Because you see this, when you take the product, this cancels with all that. So the lengths disappear. Only the angle is there. 4 times cosine square between these two. Now this is, we know it's non-negative. Well, of course this is non-negative, but we know more than that. These are integers. Because each of these guys is an integer. Product of 2 integers, again integer. So this is going to be an integer, right? But we also know cos square is always less than or equal to 1, right? So what possible integers you can have? It can be 0, it can be 1, 2, 3, and 4. That's all. Okay. Well, if it is 4, then cos square theta alpha beta is 1, which means angle is either 0 or pi. That means it's parallel, it's the same. So alpha and beta are not different roots, it's the same root, right? So we don't learn anything from that. So when the two roots are different roots, no, then the only this is not possible. You have only these possibilities. That's and then one can write down what are the possibilities. That is summarized in the table. In the table in page 95. So for each of these possibilities, so you have, of course, so you have, I'm just writing on the table, n alpha beta and beta alpha, and then the angle theta alpha beta for each of these choice, and finally the relative size. So relative size, relative lengths between relative length between alpha and beta. Huh? Because okay. Because once you have fixed this any one of these numbers, then you know what is cos squared theta alpha beta. But then if you go back here, this will tell you what is the ratio between length of beta and alpha. No? If you substitute that value of cos theta alpha beta. So you also know the lengths, the ratio of the lengths. And then the alpha string through beta. So these are the table. So let's take the first case. Say this, when it is 0, you can't say much. In fact, you cannot say anything at all. When this is 0, so this is 0, then because you see both have to be 0 then, right? Because it doesn't matter. I mean, surely this denominator is never 0, right? It's a length square of a non-zero root. So that's certainly not 0. So if it is 0, it just means the cosine theta alpha beta is 0. So therefore both are 0. And then you can't say anything. I mean, there's nothing more you can say. The only thing you can say is theta alpha beta is pi by 2. Pi by 2 or 3 pi by 2. It doesn't matter. 90 degrees, perpendicular. Okay, then if you take n alpha beta equal to +1, and n beta alpha is also then +1, because the length, so product must be non-negative. Then the angle is pi by 3. Okay. Because cos squared theta is 1. So if this is 1, then means cos squared theta is 1/4, right? So cos theta is 1/2. Okay. And if it is 1/2, then I think it's pi by 3, 60 degrees, right? Cos 60 is 1/2. So that's pi by 3. And in this case, you see that if you substitute, if this is 1, then so if this is 1/2, cos theta alpha beta is 1/2, right? So this cancels, and length of beta is the same as length of alpha, right? So this means length of beta is equal to length of alpha. And the alpha string through beta will consist of beta and beta minus alpha. Because we have taken n alpha beta equal to 1. Right? So before, from the previous discussion, then beta minus alpha must be there. Then similarly, you can put -1, -1. Product must be plus, but -1. Now it's 2 pi by 3. So 120 degrees. It becomes a negative, right? Cosine becomes negative. More than, between 90 degrees and 180 degrees, cosine is negative. So again, the length is the same. And this time you'll have beta and beta plus alpha from the previous discussion. Because this is negative, so beta plus alpha. Now let's take the case 2 and 2 and 1. You cannot have 2 times 2, because that will be the 2 times 2 will give you the 4, right? But that we saw that means alpha and beta are the same root. So when we're talking about 2 different roots. So you have 2, 1, Of course, it doesn't matter, 1, 2 or 2, 1, you can get this. So you have 2, 1, then the angle is, so if this cos squared theta, so this n alpha beta is 2, so this is 2. So what does it mean? Cos squared theta is 1, the product, you see 2 times 1, right? 2 times 1 is 2, so this becomes 1/2, cos squared theta is 1/2, so cos theta is 1 over root 2, which means 45 degrees, right? So pi by 4. Pi by 4. And this time, if you substitute this n alpha beta, this is 2, right? We are saying this is 2, and this is 1 over root 2, so it is root 2. So what does it tell you? Beta is 1 over root 2 of alpha, right? The length. So this is, so beta, no, is it? It's 2. No, beta is root 2. Beta is root 2 times. So beta square is 2 alpha square. Yeah, because so I mean that statement was that this is now we are saying is 2. So cos theta is 1 over root 2. So this becomes root 2, right? And this becomes root 2. You can divide, so it's root 2, right? So beta is root 2 times alpha. So beta square is 2 alpha square. And here now the chain goes from beta, beta minus alpha, beta minus 2 alpha. And then finally we have 2, again minus 2 minus 1. This is simply 3 pi by 4. This is still true. And this time it is beta, beta plus alpha, beta plus 2 alpha. And finally, we have the case when the product is 3. I mean, this product n alpha beta and beta alpha is 3. But then you see each of them have to be integer. 3 is a prime number. So the only possibility is one of them is 3, other is 1. Right? So you have again a sign. You can have 2 different signs. You can have 3, 1 or minus 3, minus 1. 3, 1. So what is the, so this product is 3. So this product is 3. So then it's 3/4. So cos theta is root 3 by 2, which means 30 degrees, right? So 30 degrees is pi by 6. So this is pi by 6. And here it is the pi minus that, so which means 5 pi by 6. And the length squares are, so now we have, so this is now root 3 by 2. So this is root 3 by 2. Right? Cos theta alpha beta is root 3 by 2. So 4 over root 3. Beta is 4 over root 3 alpha. And no, 4 over root 3 equal to 3. Huh?
So
No, 2.
So times.
Yeah, there is a 2 times root 3 by 2.
Yeah.
Right? So 2 cancels.
It should be equal to 3. Equal to 3.
Is equal to 3, correct. So root 3. Sorry. So it's 3. So beta square is 3 alpha square. And this is the same. And this time the chain will be beta, beta minus alpha, beta minus 2 alpha, beta minus 3 alpha. And in the bottom case it will be plus, everything will be plus. That's the table. In particular, you see that any chain cannot be bigger than 3. Bigger than, I mean, so this has, you see, four guys, right? Beta, beta minus alpha. It cannot be more than 4. Because more than 4 is not allowed here in these numbers. So that's all. So now all of these things, as we already saw, this alpha chain through beta is simply looking at the SU2 generated by alpha, X alpha, right? The SU2 subalgebra generated by alpha, and you decompose everything else in representations of this SU2. So what this is telling you is that for each of these roots, if you look at the SU2 representations, it cannot be more than a what is it called?
Quartet.
Quartet. So meaning spin 3/2. So nothing can be higher than spin 3/2. So this is like spin half because it's a doublet. This is triplet, so spin 1, and this is 4, so spin 3/2. It cannot be more than that. This is already quite a powerful statement. Yeah, so now, okay. Right. Good. So, okay. So now let me continue with this and come to. So that to make more progress, what we should do now is again like in the SU3 case. SU3 case we knew all the roots, right? Here we don't know all the roots yet. Right? We don't know all the roots, but we have just this relations between two roots, pairs of roots, right? These are the only possible numbers you can have, these n alpha betas, and these are the only angles you can have. And given these angles, you also have fixed ratios for the length. So this is the only information we have so far. But now to look at the full Lie algebra, what we should try to do is, just like in SU3 case, we had a notion of positive roots and simple roots, right? So we want to introduce something like that now in complete generality. So first of all, we would like to define what are positive roots. In the SU3 case, what we did was we said, okay, we had these roots, I mean this hexagon, and we just arbitrarily draw some hyperplane, let's say. Okay, hyperplane in this case is just a line. But in higher dimensional Cartesian subalgebra, it will be some kind of hyperplane, which divides, which has a property that this doesn't pass through any roots, any non-zero roots, apart from the 0, of course. And no non-zero root is lying on inside this hyperplane. Then you say, okay, one side I declare to be positive, other side I declare to be negative. So can we say this in a more, this is what I'm going to say is actually equivalent way. So in Cartesian subalgebra, when we define Cartesian subalgebra, we always said that at least there is one regular element, right? That was to avoid the pathologies that could arise. If you choose, if you don't put these restrictions, you can arrive at some, very strange quote-unquote Cartesian subalgebras, which you cannot even diagonalize. So this is just to ensure that everything goes smoothly. So let's suppose H0 is a regular element. Regular element of Cartesian subalgebra of H. H will always denote Cartesian subalgebra. So what it means is that, as you saw, it has the minimum number of zero eigen values, right? But that is the same as saying that alpha of H0 is not equal to 0 for all alpha belonging to delta. Okay. Why? Because, I mean, you see, this guy anyway has 0 eigenvalues, but the Cartesian subalgebra, because Cartesian subalgebra, they commute with each other. So adjoint, if you look at the adjoint of H0, add H0 certainly has 0 eigenstates, 0 eigenvalues, and the number of these eigenvalues certainly is greater than or equal to the dimension of H, the Cartesian subalgebra, because they all commute with each other. So that is for sure there, right? But this condition is saying that, therefore, I mean, this H0 does not give you 0 eigenvalue with any of the non-zero roots, right? Because add H0 acting on, say, X alpha is the same as the H0 commuted with X alpha, and that's the alpha H0 times X alpha. So if this is not 0, then you see none of the non-zero roots correspond to 0 eigenstates of H0, right? So this is it. It has no more. The 0 eigenstate is only equal to just the Cartesian itself, right? That's the minimum. There's nothing, you cannot have. So this is a regular element. Because regular element was defined as something which has a minimum number of 0 eigenstates, okay? And this satisfies that. So I'm guaranteed that such an element exists. Actually, there are infinite number of elements. This is just to be on the safe side. We are just saying at least one exists. But actually, most of them are this type. Most of them are regular ones. In fact, from this picture, you can see the only irregular ones would be the one which would correspond to one of these conditions equal to 0. But this condition will be restriction, right? It will not be a generic point in the Cartan subspace. So generically, it will be all regular elements. So anyway, once we have that, then you can just define the positive and negative as those alphas, such that alpha H naught is, since it is not 0, it can be positive or negative. That's it, right? So either alpha H naught is positive. By the way, now I'm always talking about HR, I should say HR, the real, where all the metric is positive definite. No? Once you, in the full complex Cartan subalgebra, it was not. But it's when you restrict it to the real Cartan subalgebra, then it was positive definite. So all these discussions are now with respect with the real Cartan subalgebra. So this H naught is in the real. H naught is in real HR. So alpha H naught is either greater than 0 or alpha H naught is less than 0. Since this is not equal to 0, these are only two possibilities. Right? So all the roots which have positive, where alpha H naught is positive, you say that such alphas, so if alpha H naught is greater than 0, then alpha belongs to what we call delta plus. Delta plus meaning positive roots. And if this is the case, then you say then alpha belongs to delta plus. Okay? So this way you split. So of course you have infinite ways of splitting because you can choose different H naughts. For each of these choices, you may get different positive roots, but it doesn't matter. The whole analysis is invariant with respect to what you choose. So delta plus in the notes we have put here superscript. Okay. Okay, that's a positive roots. Now we need to have a definition of simple roots. Because like in SU3, you remember when we define this positive roots, we had alpha 1, alpha 2, and alpha 3. Right? But alpha 3 was the commutator of alpha 1 and alpha 2. Right? So if you knew how alpha 1 and alpha 2 behaved, then from that, if you know exactly what are the matrices for alpha 1 and alpha 2, then alpha 3 you can immediately obtain. Right? So you're not getting any new information from alpha 3. Right? So what we want to look at to find out is so-called notion of simple roots, such that if you know all the properties of simple roots, then you can obtain everything else. Okay, that is the idea. But okay, so now suppose alpha 1 and alpha 2 are in delta plus, and let's suppose alpha 1, alpha 2, and let's say alpha 3 are in delta plus, and let's suppose alpha 3 was the commutator of alpha 1. X alpha 3 could be written as a commutator of x alpha 1, x alpha 2. Proportional to some number is not important. Non-zero number. So suppose it was the case. Okay. Then, so what would that mean? You know that the weights, the roots add up, right? So then this would imply that alpha 3 is equal to alpha 1 plus alpha 2, right? So what we are seeing is that, if I have a positive root, which can be expressed as a sum of two positive roots, then this is the properties of this I can obtain from if I know the properties of these guys, right? So you don't want to consider those guys, which can be expressed as sums of two positive roots. So this motivates a definition of simple roots. So simple roots are the ones that cannot be written as sum of two positive roots. So you remove all the roots, all the positive roots which can be written as sum of positive roots, remove them. Then what is left over is the simple roots. Okay. So that's the definition. Now this is, of course, this in this abstract way of defining it, I mean, it's not at all obvious. In SU3, we had alpha 1 and alpha 2, the two positive roots, two simple roots, right? Alpha 3, remember this, this picture, we had, this picture, alpha, this was alpha 1, alpha 2, alpha 3, right? Sorry, the picture is not very good, but something like that. Huh? And alpha 3 was the sum of these two. Then we said the simple roots are just these two, because alpha 3 can be written as a commutator of these two, x alpha 3. Okay, in this case we immediately see there are two alphas, two simple roots. This is a two-dimensional space. So and these two simple roots span the space, right? But now in this abstract way of saying it, how do I know that this way of obtaining the simple roots gives you exactly this number of simple roots? Number of simple roots should be equal to the dimension of the Cartman algebra, right? Because these are living in the dual space of the Cartman algebra, but the dual space has the same dimension as the Cartman algebra, right? So you must have the same number as the Cartman algebra, dimension of the Cartman algebra. So it's not obvious at all, right? But one can prove it now. So that will be the next theorem. Yeah. So, okay. So, any question up to this point? Because then I will erase some of these. Okay. So the theorem 14.1. And so by the way, this set, there is, we have to give some notation. So define the simple roots are this, and we call this the set of simple roots. We denote is denoted by capital sigma. Let me just use same notation. Capital sigma. Just like capital delta was a set of all roots. Delta plus was a set of all positive roots. Now this is the set of all simple roots. So the statement is, suppose alpha I and alpha j belongs to sigma plus, sigma. Suppose. So if this two belong to sigma. Of course I am thinking of this as two different roots. Then alpha I minus alpha j does not belong to the delta. I mean, if they were the same, of course it will give you 0. Alpha I minus alpha j will be 0. That will be the Cartman algebra. But delta usually you talk about as a non-zero root, a set of non-zero roots. But anyway, I'm talking about two different. So the difference is not equal to 0. So that's the statement. Then, okay, there are several things, but maybe one can go one by one and then proceed. There are four statements here. Yeah, actually this is...
contradiction.
Huh?
Contradiction. By contradiction.
By contradiction, yeah, exactly. So by contradiction. Okay, so suppose it is not, so a contradiction. So assume that alpha I minus alpha j is some, let's say beta, let's call it beta, where beta is an element of the roots. So beta can either be, so there are two possibilities. So two possibilities. So beta can be either in delta plus or beta can be in delta minus. Two possibilities. Of course, cannot be both true, right? Because there's a clear separation of delta plus and delta minus. So suppose beta, no, so we have to take both these cases. So either this or that, or so if it is A, then then we have alpha max. So that's this I can write it as alpha I is equal to alpha j plus beta. But that's a contradiction, because then this is a positive root. I mean, every simple root is of course inside the positive roots, huh? Because here the discussion is about all the positive roots. Simple roots are the ones. I mean, are those? Sorry, I should have written. Are those positive roots? So the simple roots are. This is inside delta plus. Okay? Simple roots are subset of delta plus. So this is of course delta plus. This is also delta plus. This is also delta plus. But here we have a contradiction, because by assumption we are saying simple roots cannot. This is a simple root. It cannot be written as a sum of two simple positive roots, right? So that's a contradiction. So this is not possible. And if it's B, then I can write alpha I. Suppose it was a negative root, a delta minus. Then minus beta. This would imply that minus beta is in delta plus. Okay? So I can write this as alpha I plus beta equal to alpha j. I mean, so. Alpha I plus minus beta, okay? Because I mean this equation I can write. I mean this equation I can write as alpha I minus alpha j equal to minus beta, right? I haven't done anything. Now this is a positive root. Minus beta is a positive root. Take it on the other side, and bring this on the other side. So then you have alpha I plus minus beta equal to alpha j, right? This is a positive root, this is a positive root, so we have the sum of two positive roots is this, but this is a simple root, so it cannot be. So this is a very important point. This alpha I minus alpha j cannot belong to the positive roots. To the roots actually, anyway.
Do we know that for every negative root there is a positive root and vice versa?
Yeah, because we know that if there's x alpha, there should be x minus alpha, otherwise non-degeneracy is a Cartman killing form, right? I mean, remember that we said that v of x alpha, x beta is equal to 0 if alpha plus beta is not equal to 0, right? So if I fix an x alpha, then I look at all possible beta, and let's suppose for none of the betas this relation is true, then x alpha is a degenerate vector. I mean, is a vector which has dot product 0 with everything else. That means B is not invertible. Okay. So that implies that there must be some beta such that this is equal to 0, which means beta is equal to minus alpha. Yeah. Okay. Yeah. So you see that this is indeed, you remember this again, the SU3 picture is always good to remember. So we had alpha 1, alpha 2. Alpha 1 minus alpha 2, so this is minus alpha 2, right? Yeah. So this plus that would be somewhere here, but that didn't exist. No? On the other hand, if you take alpha 3, this is alpha 3, alpha 1 minus alpha 3, so alpha 3 minus alpha 3 is that. This plus that is this, right? So that was quite. But this is just a general thing. It is not just an accident in SU3. What we are saying is this is completely generic. Okay, that was the first statement. Second statement is, the second point was, yeah, if alpha I, alpha j belong to sigma, then alpha I, alpha j in a product must be less than or equal to 0 for all I not equal to j. Because for I equal to j, of course, this is a positive definite metric, right? If alpha I will be positive, right? But the statement here is for not the same. There are different simple roots. So these are different. Alpha I is not equal to alpha alpha j. Okay. So how do you prove this? It's just a consequence of looking at the chain. So if you look at this chain, alpha I string through alpha j, then we had this formula 2 alpha j alpha I divided by alpha I. This was P minus Q, where P was, this chain was alpha j minus P alpha I all the way up to alpha j plus Q alpha I. Right? But already we know that alpha I plus alpha j is not a root. Alpha I plus, alpha I minus alpha j is equal to does not exist. So we have alpha j here. So these guys are not there. And you remember that there was a proof that alpha j minus alpha I does not exist. This we already showed, this doesn't exist. But if you all remember, one of the theorems last week we did was to show that this chain cannot be like bits of chains. There must be just one chain. So if this is not there, none of those guys are there. Okay? So all these are not there. That means P is 0. That means P is 0, Q can be non-zero. Right? So we are saying, where was that? So P is 0, Q can be non-zero, but that means since this is equal to 0, we are saying this is less than or equal to 0. That's that statement. It's always negative. Third, what's that? So the third statement is all the elements of sigma. Let's say, so suppose sigma is the set of the simple roots, right? Alpha 1, alpha 2, whatever, these roots. So these are the simple roots. So we are saying that, these are, all of them, I put all of them. Suppose it goes all the way up to alpha k. Suppose there are k simple roots. Then we are saying that the statement of the third statement is that these are linearly independent.
Isn't it the same as the definition?
No. There's a statement, there's a theorem one has to prove. Linearly independent.
Isn't it the same as the definition of those simple roots? That the definition that they shouldn't be obtained through other roots. So
yeah, that is true. But it was only it was a sum should not be.
So
I'm sorry. The difference is not. What was the statement? The difference is not in the roots. So what we are saying is that alpha I cannot be expressed as some, say, beta plus gamma, where both of these guys belong to delta plus.
Right. So this addition isn't the same as the addition that exists in the linear independent relation.
Well,
it's the same.
It's not obvious. This is basically coming to the statement, right? That what if I had several roots? Let's say I have a two-dimensional. So SU3 we are two-dimensional, right? Cartman subalgebra is two-dimensional. But what if there were various roots like that, simple roots like this, let's say, where none of these things can be written as a sum of the other two. We don't know yet, no? So, but now we are going to show. So, in this case, they will not be linearly independent. Because, maybe when I give the proof, it will become more clear. So the proof is the following. Okay, so let's suppose that is, so there is, so again, contradiction, assume the opposite. So that they are linearly dependent. Assume they are linearly dependent. They are not linearly independent. Not linearly independent. Okay. Then there must exist some numbers, some quantities, let's call it xi, alpha I, equal to 0 for I going from 1 up to k, where k is the total number of simple roots. There must exist something like this, where not all of xi's are equal to 0 simultaneously. At least some of the xi's are not 0. So now suppose, okay, I mean in the proof, okay, if you look at the proof, we have used the notation ni alpha I. Ni gives you the wrong impression that ni are integers. No? So that's why I'm using this xi. Xi is just arbitrary real numbers. Okay. Now it could be, okay, some of these guys may be 0, but some of them may be positive, some of them may be negative. Okay. So let me just call those guys which are positive as xi, and then those guys which are negative, I just explicitly write -1, minus, let's say x hat, I don't know, what shall I put, some I, say m. So here you have, I mean, so we have this x1 alpha 1, x2 alpha 2, x3 alpha 3, etc. Some of these coefficients may be positive in this equation. Some of these coefficients may be 0, but then they don't enter at all in this equation. And some of them may be negative. Okay. So the negative guys I'm writing explicitly like minus x hat. So now x hat is positive. Is that clear? So now I can write this equation in the following way. Xi alpha I, where now this sum is not going from 1 to k. It is just going from whatever, I mean, those indices for which these coefficients are positive. So I'm just writing like this, sum over. So there's a range I'm not specifying, because it just means just take all the positive terms, keep them here. All the negative terms, take it to the other side. So this is now will be x hat m alpha m. And this alpha I, this range of m and I are obviously different range, right? Because I mean, either the coefficient is positive or negative. If it is 0, you just throw that out, because that simply doesn't enter in the equation, right? So the positive guys will appear here, and negative guys are appearing there. So this index I and m cannot be the same, right? I mean, if say alpha 2, the coefficient is positive, and alpha 3 has a coefficient negative, alpha 3 is coming there, but alpha 2 is staying here. You cannot have that alpha 3 and alpha 2 both are in both places, no? You see? So there's no... Okay. So now let's do the following. Let's take the square of this. The sum over xi alpha I with itself. Okay, the inner product. But that's the same from this equation is the same. Also, by the way, so these are not positive. This is positive, because I mean, this negative guys I wrote it as a negative minus of a positive guy. So these are all positive now. So by using this equation, I can write this as sum over xi alpha I, and from this one I replace by that. So x hat m alpha m. Okay. So which is the same as so this is the same as I open up, because this is bilinear, the inner product is bilinear. So that's the same as sum over xi, xm, x hat m of alpha I, alpha m. But we have already shown in number 2 that alpha I with alpha j, when this I and j are different, this is always less than or equal to 0. Right? So each of these quantity is less than or equal to 0, because I and m are never equal, right? Because that's why I was saying that either they are here, some index will be there only here or there. No? So these are definitely different roots. Okay? So this is going, each of these term is going to be less than or equal to 0, each of them. But this is positive. Okay? So this is less than or equal to 0. On the other hand, this is the inner product of the same guy, is positive definite, right? So this is greater than or equal to 0. Like greater than or equal to, actually strictly greater than 0. Okay. Strictly greater than 0 because this is not, I mean, unless this happens to be 0. Each coefficient has to be 0 now, right? So that is a contradiction. Because on the one side, from this equation, we are saying this is going to be less than or equal to 0. Okay? But other than a positive definiteness tells you this is positive. So that's a contradiction. So this relation cannot be there. I mean, the only way this can be satisfied is if all the xi's are 0, which means they are linearly independent. Well, now I'm really talking about the real numbers. You see, because when we talk about the roots and so on, it could be that you have, some, maybe let's say in 2 dimension, say I have two roots. Of course, we know in this case they are not possible. In this case, we have other theorems which already show it's not possible. Let's suppose I have a 3-dimensional system. Kashmir subalgebra is 3-dimensional. So I have, in order to be linearly independent, these guys must be spanning they cannot be all in a plane, right? So they cannot be, the statement is that it cannot be that, so there's a third direction is here. So I cannot draw it here. So they cannot be that all the 3 are sitting in the same plane. No? And this may not be, this may not be equal to the sum of that. Some of these guys will be something, maybe here, maybe here. But say this is something else, two times, not 2 times or something, maybe some different direction, who knows? We don't know yet, right? So this is to avoid that. Here when we talk about not simple roots, there was coefficients are always positive integers, right? You say alpha plus beta. So in this case, coefficient is +1 +1. But now we are talking arbitrary real numbers. It need not be 1. It can be 0.0001 or whatever, So this is really saying that. Just the simple roots doesn't tell you that these are linearly independent. Maybe this guy cannot be written as a sum of these two, perhaps. But that does not mean that this is linearly independent when you allow the real coefficients. So, but this is stronger statement.
Could we say that we can, when we write them that way, we could express one of the simple roots here, the simple positive roots here, as a sum of other roots?
No.
Other.
No, we are not saying that because take for example, let's say suppose this range was just 1. Let's suppose the I was only for one guy it's positive. Xi is positive. Let's say x1. Only x1 is positive and everything else negative. Suppose this case. Then what would it say? So it would say that x1 alpha 1 is equal to all the x hat m alpha m, right? Where this m is not equal to 1. And some of them may be 0, but when they are not 0, they are positive. That's all I'm saying, right? But then I can divide by x1 because x1 is not 0, so I can divide by that. Then we are saying alpha 1 is the sum of the other simple roots. But coefficients are not integers necessarily, right?
So it's necessarily have to be. Could we write a simple rule as a sum of non-integer coefficient for other roots?
No, that will be difficult to use because roots, you cannot multiply a root by some arbitrary real number. No? So we are saying, alphas are the eigenvalues. Right? Eigenvalues are fixed. You cannot just multiply by some number and get another eigenvalue. No? I mean, you see, eigenvalues are totally fixed, right? There is no, eigenvalues are not in a vector space. I mean, eigenvalues don't form a vector space, right? If I give you an operator, it will have some definite eigenvalues, some eigenvalues, right? If you say k by k matrix, and you ask what is the determinant, I mean, if you look at some matrix M, and look at this eigenvalue problem, okay, this is an identity matrix. So this says, suppose it's k by k matrix. So you just look at the this equation, right? And then this is what, this will be a, when you open it up, it will be a kth polynomial, degree k polynomial, right? So this will be some degree k polynomial in lambda, right? And when you solve that, it will be k solutions, right? Yeah. But those solutions, it's not that you can just multiply by any number. That will not be solutions, right? So, so alphas are something fixed. I mean, you cannot change. I mean, in SU3, let's say take the SU3, this alpha 1, right? 1.1 times alpha 1. Okay, is it a root? No, it's not a root, right? But when we talk about whether it's spanning the vector space, it means, can I express any vector in this space as linear combinations of these simple roots with real coefficients? We are not saying that those are eigenstates, eigenvalues.
I see.
Okay. Okay, so this tells, so already the fact that they are linearly independent, that is saying this k must be, k cannot be greater than the dim of h, right? This implies, so this, what we are saying that these are linear, this we have proven that this is linearly independent, therefore this implies this k must be less than or equal to dimension of Cartan subalgebra, right? Cannot be more. Because if it is more, there is no way it can be linearly independent, right? Okay. So, what the last point. Now so finally we need to prove that actually this k is yeah.
Is our dot product essentially the same as we have in the root?
Codes, yeah. It's by definition B of H alpha expression.
I mean, for example, if I multiply A1 with A3, will I get the 60 degrees as an angle or something different? In SU3 case.
SU3 you have 60 degrees, 120 degrees, yeah.
Yeah, what I see is the same thing as we calculated. So then, for example, can you choose A1 and A3 as the simple roots? I think it's not allowed.
Alpha 1 and alpha 3 you cannot, but from this definition.
How come I not?
Because we saw that alpha 1, I mean, if you look at, what was that? Because alpha 3, you could write it as alpha 1 plus alpha 2. In fact, the simple roots was defined like that, right? Any positive root which can be expressed as sum of two positive roots, you throw that out, right? And then, so simple roots are the ones which cannot be expressed as sum of two positive roots.
So we have all roots in the root set, and by just this definition, we can see which ones are the simple roots, exactly. And there is no choice for us to choose.
Yeah, once you decide what are your positive roots. Mm-hmm. So the positive roots, you needed to choose some H0, right? Remember H0. So once you choose that, then you know what are the, this is for the, I mean, it's not for any roots. No, this alpha 1 and alpha 2 are in positive. So simple roots are any alpha belonging to sigma is such that alpha is not equal to some beta plus gamma, where beta and gamma both are in delta plus. Because even here, I mean, if I didn't have this condition that both are in their positive roots, then I mean I can write this guy as this alpha 1, I can write it as a alpha 3 minus alpha 2, right? But minus alpha 2 is a negative root, once you have decided what are your positive roots, no?
So once we decide what are the positive roots, then the basis for the root space is fixed. We cannot change the basis.
Exactly. Yes.
And can I say that if the angles are the same, the roots must at least have a 90 degrees angle between themselves to make the inner product negative.
I mean, 90 degrees will be 0.
Bigger than
Bigger
that.
than, yeah.
For the A3 is
That's
not that big, so we cannot take it because of that condition.
Exactly. Yeah, this condition, that equation was the alpha I, alpha j is less than or equal to 0. It is exactly saying that between two simple roots, it will be always angle between 90 and 180 degrees, right? I mean, less than 180. 180 would be parallel, so that is out of question. So, or more than 90. 90 or more.
So if we had a third dimension to our root space,
Yeah.
for example, to look the same as a SU3, and the third is not looking like this, but a little bit
Yeah,
like this.
Yeah, exactly. Yeah. In fact, I mean, yeah, you could see. I mean, from that point of view, you see that once you have accepted this, I mean, in 2 dimension, if you draw, I cannot have three things in the 3 simple roots, because it cannot be that, okay, this angle is obtuse, right? It's the correct word, right? More than 90 degrees is called obtuse, right? So these are obtuse. We want 3 lines which are all obtuse with respect to each other. That's not possible, right? So that, but in 2 dimension you can draw. You have arbitrary dimension now. I mean, how is it? But yeah, but the final classification, Dinkin classification, is actually done exactly like that. You work with an arbitrary dimension, but then you basically show that geometrically is not possible, to have so many obtuse angles, so many of the things are ruled out, and then you see that the only possibilities for the leftover are the SUN, SONs, SPNs, with a few finite number of exceptional groups. SON, SPN, SUN are infinite series, right? Because n is arbitrary. But then there are a finite number: E6, E7, E8, G2, and F4. Just 5 of them. So that is done exactly by this procedure. Because once you have Euclidean geometry, you can use the geometric notions, and then you say, okay, can I? I mean, you ask, okay, somebody says, okay, I have some set of simple roots, and so what is the classification? I mean, once you specify the simple roots, basically you just need to specify these numbers. These numbers, let's call it, I think it's called AJI or AJI. This is called the Cartan matrix elements. You specify these numbers. Once these numbers are specified, your algebra is unique. I mean, you fix the algebra completely. Okay? But then the question arises, could I have chosen arbitrary numbers? Integers, they're all integers, of course. But could I have chosen, and even we know that it's going to be less than or equal to 0, right? When I is not equal to j. So when I is equal to j, this number is always 2. So the AII is always 2. That has no information. The non-trivial information is the off-diagonal guys. And off-diagonal guys are going to be negative, I mean non-positive. But then you ask the question, can I put any numbers? And suppose I have 2 by 2. I mean, suppose rank is 2. So this I and j can only go from 1 to 2, right? So we know diagonals are 2. And also we know that you can have, these numbers are bounded by 3, right? This we already saw from that 4 cos square theta equal to integer. That can be only 1, 2, 3. And so this can be either -3, -2, -1, whatever, with possibilities. But then you ask, are there all possibilities? I mean, could I have chosen -3, -2, or various possibilities? And you find it's not always possible. And the way you prove it's not always possible is exactly through that argument. If you say, okay, there are so many obtuse angles like this with so many lengths, because this also fixes the lengths, relative lengths, no? Then given these lengths, can I construct these 3 to be non-linear, all of these guys to be linearly independent or not? No? And many times you come to the conclusion it's not possible. Then it's not allowed. So this way you classify all the possible allowed Cartan matrices. And that turns out to be just this SUN, SON, SPN, plus a few exceptions. Hopefully today, no, it's already time. Oh. I wanted to give you one example which is not in the SUN, SO. Is totally different. It's, in fact, I'm not sure. Historically, probably that Lie algebra was discovered by this method. Historically. I'm not sure, 100% sure about that. Because it doesn't come out as some kind of a symmetry of some systems, no? Because SO, I mean, we understand the symmetries, no? I mean, all these things come from symmetries. SON as rotation, SPN as the canonical transmissions, SUN as again rotations in the complex space with the Hermitian metric. So these are all have natural origin, no? But this G2 doesn't have any natural origin. Okay. Now, so then this last point. So the last statement I wanted to show you to go through. Yeah. So the statement is this. So now, I mean, so far now we know K is less than or equal to D match. But if you want to say that this spans the sigma, then it must be exactly equal. K must be equal to the dim of H, right? So how do you prove that? So for this, it is enough to prove that all the roots can be expressed as sums of simple roots. Because we already know the root space, all the roots spans there, right? So if I can show that all the roots, this you can obtain all the roots from the simple roots, then you have shown it, right? So that proof, that's the last statement. So the last statement is, yeah, so, yeah, so the statement is that if alpha, so any alpha belonging to delta plus, I can write as alpha equal to sum of say ni alpha I, sum over I with ni greater than or equal to 0. Yeah. So this just goes back to an inductive procedure, because I mean, okay, if alpha is a simple root, then it's obviously true, right? Because I mean, if alpha is one of these alpha i's, then you just take that ni equal to 1 and everything else 0. Right? That's okay. So the issue is now when alpha is not a simple root, but it's a positive root. Then by definition, this positive root must be a sum of two other positive roots, right? And then you can so say alpha must be equal to some beta plus gamma, which is again the some positive roots, delta pluses, each of them, beta, gamma. But now if this is if these are simple, okay, fine, right? Then we have already proven. If it's not simple, then again this can be written as a sum of again two positive roots and so on. So this procedure keeps going until you end up. Because anyway, you have a finite dimensional system, right? I mean, this is our finite dimensional system. At some point, you cannot write anymore as sum of simple roots, sum of positive roots. Apart from, I mean, you'll arrive at the simple roots. That's all. So each, I mean, this guy, if this is not belonging to sigma plus capital sigma, then this again I can write as some beta 1 plus beta 2. No? And you keep going. This gamma again, if it is not, then gamma is gamma 1 plus gamma 2. Now again, if these are not simple, then again you can write, keep going. But since it's a finite dimensional system, eventually you'll arrive at writing everything in terms of simple roots. So that's the idea. And so delta plus, if you can write like that, then obviously delta minus also, because you can just have to put a minus here, right? Because for every, if alpha belongs to delta minus, then minus implies that minus alpha belongs to delta plus, right? And if minus alpha I can express like that, then therefore alpha I can express also. So all the roots can be expressed as a combination. Actually, this says even more than that. I mean, for the spanning it here, ni need not have integers, but this procedure will obviously going to give you integers. So all the roots can be expressed as linear combinations of simple roots with integer coefficients, where for positive roots, these are all, positive, non-negative. Right? And similarly, for the negative roots. So this is that's the procedure. Negative roots all be non-positive.
And all the linear combinations are done by integer multiples.
Yeah. Because when we said that sigma is a set of guys which cannot be written as a sum of two roots. But I mean sum of roots meaning two roots meaning that's with the coefficient 1. Just take the sum of two roots. Okay, so that's that. Now what can I do?
So we know that the dimension of simple roots are exactly equal to the dimension of H.
Yeah.
By this procedure.
By this procedure. Because it spans by it spans. And we have shown it's linear independent.
It spans, but it's actually not a continuous vector space. We can only add integer multiples.
No, that is to get the roots. That is to get all the roots, right? But we already know that the roots, the set of all roots span the entire space when you allow the coefficients to be non-integers, right? I mean arbitrary real numbers. Dimensionality is just that. No? I mean these are some specific vectors. I mean you see if I multiply this SU3, this guy, SU3, let's say if I multiply this by 1.1, it is not a root. Fine, but I mean, when I'm not talking about spanning, I mean really spanning the entire space where you now allow to multiply by arbitrary numbers. They have no interpretation as eigenvalues. True, they have no any other point, arbitrary point, this will not correspond to any eigenvalue. Right? But this is simply a question whether how many independent vectors are there basically? Is it?
Do we directly know by this procedure that we have in the end dimension H vectors that are constitute the simple roots?
Yeah.
I mean, maybe we could end up with all roots with a number less than dimension of H, and then when we allow to coefficients to be real, they do not span the root space.
Yeah, that is. So let's see. I mean, but what if suppose I take the dimension 3. I mean, dimension of Cartan, let's say SU4, right? And what if all the simple roots happen to be lying on a plane, right? So we have 3 simple roots, but that doesn't mean that it's spanning the whole thing, right? Yes. So one is just trying to avoid that. So there are 2 statements here. One, that the simple roots are linearly independent. So we are already ruling out that it cannot be in one plane, right? That one is ruling out. No, not necessarily. It depends on what is the numbers. All one is saying is this number, whatever this set is, this is linearly independent.
Well, I'm asking this something like this. We have a 3-dimensional root space,
yes,
and we can reach every root with 2 simple roots. Is it possible? That's the question.
How can it be 2 simple roots when you keep adding them up? They're only going to span a 2-dimensional space, right?
If you think it like already a continuous space, we couldn't reach some points.
But integers are subsets of real numbers, right? If the real numbers do not let you reach in the 3rd direction, then integers certainly will not, right?
How do we know that the next root is outside of that plane? In the 3.
So you are saying that it could be that all the roots are in a plane.
Actually, the root space is a 3-dimensional.
Right, but this was one of the theorems we proved before, that for the semi-simple algebras, the root space, this was, I don't know which theorem was it, that it spans the entire space, Hilbert space, H star, which was one of the,
very beginning.
Yeah, it was, which is using again the non-degeneracy of the Cartan.
The extra dimension would cause the metric to be degenerate.
Yeah, correct. Yeah.
There is no
exactly
empty direction.
That's right. Yeah. This will not be, once you drop the semi-simple, then it is not true. I mean, then you can have such situations. For example, take U2. U2 which means basically SU2 plus U1. That U1 is free. I mean, so Cartan is really 2-dimensional because SU2 is a Cartan, subspace is 1-dimensional, and the extra U1 which commutes with everything is also 1-dimensional. So this is a 2-dimensional Cartan subspace, but SU2 non-zero roots have always been one line. So that's an example, and that's not a semi-simple algebra. Right. So semi-simpleness is crucial. Invertibility of Cartan killing form is crucial. So now, I don't know, I wanted to do this G2, but is going very slow.
Maybe next lecture we can start earlier and
We want to start earlier and go on. But I mean, at some point, there's also concentration span, right? I mean, after 1.5 hours, it becomes difficult to concentrate any longer, no? But if you wish, we can start earlier, then have a break and then continue. We can do that. The morning. Yeah, one could have to check, of course, with from.
Yeah, we have the discussion tomorrow, I guess. The tutorial.
Tutorial.
Yeah, doesn't have.
What time? In the morning. One possibility is we could meet at 1, go on till 2, then have a little break, then again come back. Because it's difficult to concentrate for a long time continuously, no? Because I wanted to give this example of G2. No, basically complete all the rank 2 semi-simple algebras we can find by using that gives you some idea how you work out. I think it's not just the G2, but it gives you the procedure how, given these numbers, just the simple roots, given the simple roots and the dot products between them, how you can construct the full D algebra. It's a constructive approach. Given these numbers, those Aij or Nijs, how you construct the full D algebra. And this we can do, in rank 2 case. And then chapter 13, unfortunately I have no time. Chapter 13, but please, take a look at it, I think, for all the classical D algebras. But then I wanted to also do some spinor representations of the orthogonal group. The gamma matrices, how you construct the gamma matrices for arbitrary dimension. Because the construction of gamma matrices gives you the spinor representation, basically, fermions. So, well, let's see. So maybe we can do that. Tomorrow we can meet at 1 o'clock, go until 2, have a break, 15-20 minutes break, then we come back again and continue. I should tell Patricia to check whether this room is available or not.